Welcome. We want to look on logarithms and exponential functions. Okay, we want to start with logarithms. If a number can be written in the form of a raised to the power of x, x is the index. So then this index x is called the logarithm of y to the base of a. So in other words, we mean if y equals to a to the power of x, then x equals to the log of y to the base of a. So this expression is called an initial equation, and this equation is called logarithmic equation. So we want to look on types of logarithms. There are only two types of logarithms. Number one, we have the common logarithms. These are the logarithms with the base of 10. So they are expressed as log to base 10 of x equals to y. The second type of logarithms are the natural or the Napierian logarithms. These are the logarithms with the base of e, and e is a mathematical constant whose value is approximated to 2.7183. So they are expressed in the form of log of x to the base of e equals to y. Sometimes, or most of the times, they are written as ln x equals to y. Yes, so those are the types of logarithms we have. So next, let us move to the laws of logarithms. There are three laws of logarithms. So law number one, the logarithm of a product of two numbers equals to the logarithm to the sum of the individual logarithm of the numbers. Or we can say the other way around, that the sum of individual logarithms of two numbers or more equals to the logarithm of the product of the numbers. So for example, log of 2 times 3 is log of 2 plus log of 3. That's the log of 6 plus the log of 2 plus the log of 3. And so that's what we have. Right, the second law, the log of a number divided by another number equals to the difference of the individual numbers. The difference of the individual logarithms of the numbers in the order that it is the difference of the individual logarithm of the denominator number from the logarithm of the numerator number. So for example, the logarithm of 3 divided by 2 equals to the logarithm of 3 minus the logarithm of 2. So that's what we have. The third law is the logarithm of a number raised to a power equals to that power or the index multiplied by the log of that number. For example, logarithm of 3 squared equals to 2 times logarithm of 3. So that's what we have. So we want to move forward to the logarithmic operations. So those are the applications of the laws of logarithms. So for example, you are asked to evaluate this expression. So the first step is for us to express these numbers into their prime factors. So that is in this form. Then now next we apply the third law of logarithm. So we express as this equals to, so it is this that. So you may also be asked to solve the equation given this way. So here in this side you apply the first law of logarithm. Here we said that the sum of the individual logarithms of numbers equals to the logarithm of the product of the numbers. So we can write this one as to be the log of the product of these two numbers. So we also consider this side and we apply the third law of logarithms. So here we see from the third law, this 2 now becomes the index of this number. So it is written as, so since the logarithms of these numbers are equal, then it means that these numbers are also equal. So we equate them. So from the identities of quadratic equations that we had learned, we write, so putting like terms together and solving, we have so right. We now want to look on initial equations. So as we had looked earlier, they are in the form x to the power of n equals to y. So we use the laws of logarithms to solve such equations. So for example, you are asked to solve the following equation. 2 to the power of x minus 1 goes to the 3 to the power of 2x minus 1. So here you apply logarithms. So we start by, so the log of this number equals to the log of that number. So now we apply the laws of logarithms. So here we apply the third law. So we write in this form. So here we put the right terms together. So we write in this form. So, but this one should not confuse you with the law number 2, that is in this form. This is when you have the logarithm of a number divided by another number. But in our case here, we only have a logarithm divided by another logarithm. So we are not going to apply this law. So what we do, we write as. So we continue to solve. So putting right terms together, we have. So here we have it. So let us go to the second example. We told that the decimal gain n of an amplifier is given by n equals to 10 times the logarithm of p2 over p1 to the base of 10, where p1 is the power input and p2 is the power output. Find the power gain p2 over p1 when n is 25 decibels. So the first step, we substitute for n. So we write. So then the second step, divide by both sides by 10. So we have. So the next step, we change this equation to be an initial equation. So we have, in this form it becomes 10 to the power of 2.5 equals to p2 over p1. And this is now the power gain. And so solving it directly, it becomes 316.2. We now want to go to the second part, that is on exponential functions. So an exponential function is one which contains the constant e raised to the power of x. So as we had said earlier, e is a constant that we call exponent, whose value is approximately 2.7183. We also said that e is the base of the natural or Liberian logarithms. Right. We want now to look at the methods of solving exponential functions. So there are three methods. Method number one is by use of a calculator. For example, we are asked to solve the following. So just use your calculator. So this one equals to that answer. So right. So we go to the second method. That is the power series method. So the value of e to the power of x can be calculated to any required degree of accuracy, since it is defined in terms of the power series expressed as in this form. So we can simplify this series as this form. So these are a convergent series, and so we are going to look on examples. Now we can solve for exponential function using the power series method. So example, solve the following using the power series method. So we have e to the power of 5. So here our x is 5, so we substitute x with 5. So we write So I know you are wondering why are we finding this one, yet the actual answer is 148.413. So yeah, when we are using power series, for us to get a more accurate answer, we should use more terms as possible. So for us, we have used only the 6 terms, but if we would continue, our answer will actually near this. Yeah, so that is the idea behind the power series method. So the more terms you use, the more actual answer you get. So let us see another example. You are asked to expand this expression as far as the term in x to the power of 5. So we write the power series for e the power of x up to the term in x to the power 5. So we simplify in this form. So next step, we substitute ex in this expression with this value. So we write, no, this is one. So we write it in this form. So by opening the brackets, we have, so we now put the like terms together. Yeah, so we were asked to expand and did this the term where x is power 5. So additional powers, x power 6 and x power 7, we ignore. So our expression becomes, so we have solved. So another example, we are asked to expand this expression to 6 terms. So we start, because we know the power series for e power x, so we substitute our x with x squared. So therefore we expand this expression as, so we have expanded this expression into this form because our x now has become x squared. So we proceed. So this is the expanded expression, this one. So thank you so much for watching. Continue subscribing to our channel for more video. Thank you.